So this question tells us to find an angle theta that is coterminal with 800 degrees, where theta is in between 0 and 360. Okay, so we don't even have to know where 800 points to. We could just start with 800, okay, 800 degrees, and we're going to either subtract or add 360 from it, okay? So just intuitively, if we think about it, it says this second part here just means we want our final angle. We want the angle that we find to be in this range. We want it to be in between 0 and 360. So if we were to add 360, that wouldn't really make sense because we're going in the wrong direction, right? We'd get something crazy like 1,160 degrees, which is definitely not getting any closer to this range here, right? So what we'll want to do instead is start subtracting 360 degrees from 800, right? Because this 360 degrees just means you're kind of like taking away a full revolution, okay? So if we do subtract that, we're going to get something like 440 degrees, right? So that isn't quite within our range, right? 440 is not in between 0 degrees and 360 degrees, okay? So it's not in there just yet. But what we can do now is just apply that same idea again. We're just going to subtract another 360. So basically just go around our circle one full time again. And then we'll see what we get. Okay, so when we subtract this, we just get an 80 degrees. Okay, and that definitely is within our range of 0 to 360 degrees. Okay, so 80 degrees is going to be our answer. And here's a bonus kind of part. Or bonus idea is, let's say we were to take this 80 and subtract 360 again. It's like, wait, what? Aren't we going to get a negative number? And the answer is yes. We are going to get a negative 280 degrees, and that is allowed. This is legal. This negative sign just means we are traveling, or our angle is traveling in the clockwise direction. Because remember in the beginning I said that counterclockwise, so counterclockwise is usually considered positive, and clockwise is considered negative. So that just means we're traveling in clockwise direction. Okay? Alrighty, so here's a picture of a circle with its degrees labeled. Okay, so this is 0 degrees because we're starting at 0. It could also be 360 once we've gone around the circle once. Anyway, so even though we have a lot of numbers here, I would say that one of the most fundamental things to probably learn is this first quadrant, okay? And the first quadrant meaning this one here, okay? So that would be like the positive. This is quadrant number 2, quadrant number 3, and quadrant number 4. If we split it up into quarters like this, if I extend the lines, then we have something like this, okay? So this quadrant number 1, that just means your x and your y are positive. Quadrant number 2 means your x is negative, right? And your y is positive. Quadrant 3, both x and y are negative. And finally, quadrant 4 over here, x is positive and y is negative. Okay, if we just look at our normal coordinate system. Okay, so like I was saying, I think quadrant 1 is the most important in order to lay the fundamentals down for knowing all of the other angles on your circle. And the reason is that, let me draw like a quarter of a circle here. Okay, so we have something like this. So this is definitely 0 degrees. And this one here, we know a quarter of a circle is 90 degrees. Okay? We know a third of it is 30 degrees. We know if we move another 30 degrees, that'll give us 2/3. So this is 60 degrees. Right in between, 90 divided by 2 is 45 degrees. So that's like, that kind of slices our quarter into eighths. Okay? So just knowing these and this quadrant here allows you to kind of figure out what's going on in the other 3 quadrants as well. Because that tells us that anything else is going to be either a multiple of 30, a multiple of 60, which is automatically a multiple of 30, or a multiple of 45. Okay? So what I mean by that is saying, okay, so let's say we have our circle, right? And so here's 30 degrees. To figure out this one, you would just multiply that times 2. So 2 times 30 is 60 degrees. 3 times 30 is 90 degrees, 4 times 30, 120, 5 times 30, 150, 6 times 30, 180, and so on and so forth. Okay, you can also do the same thing with 45 degrees. Alrighty, So this, let's say we have 45 degrees, and then you just multiply by 2, so that gives you 90 degrees. Multiply by 3, then you get 3 times 45, which is 135. And 45 times 4 just gives you 180. So in that way, you can kind of just move around your circle by taking multiples of 30 degrees and or multiples of 45 degrees, depending. Okay, so just those are really important. The 30 degrees here and the 45 degrees there. So we just have multiples of those when we move around our circle. Okay, so now for a new topic, we're going to explore the topic of arc length. Okay, so let me draw a circle here. So let's say we have, this is looking like an egg, so I'm just going to try that again. Okay, so we have a circle, right? And then let's say we have an angle here. So this is our radius, right? So from here to here. This is our angle, theta. And then arc length tells you the length of an arc, basically. So this is our arc, the one that I made bold there. So S. So the formula is going to be, so S, which denotes our arc length, or length of our arc, right? So arc length is equal to our radius times the angle that we rotate, okay, for any given circle. Alrighty, so something to keep in mind is that our circumference, if we remember learning that formula way back, so circumference, which is equal to 2 pi r, this actually tells us, what is circumference? That's the distance that you go around your circle, like the perimeter of your circle, so to speak, right? So that's going one full length all the way around. So this is one full arc length. Well, we could say, let me rephrase that, arc length of making one full circle, right? Okay, and that's equal to r times 2 pi. I just changed the order, right? So according to our arc length formula up here, that says, well, r is in the same position as r. R is r, whatever our radius is, and our theta is 2 pi. And it's like, wait, what is 2 pi? I thought that the angles are measured in degrees, right? Not necessarily. I mean, yes, that's true. The angles could be measured in degrees, but they're also measured in what are called radians. Okay, and these are super useful because a lot of formulas and equations and things that deal with angles, we have to get that angle in terms of radians, in units of radians. And it's kind of funny because radians are actually unitless degrees. Okay, these are unitless. I know, it's kind of funny because it's very ironic because we call them radians, but they're unitless. What does that mean? Unitless measure of angular rotation, or of rotation, we could say. Okay? So in this sense, because like I said, so arc length of one full circle. So that means that 2 pi is in the position of theta, right? So that means when we go one full circle all the way around, our angle is equal to 2 pi radians. So that means that, let me write it on the next slide. So we said before, one full circle, in degrees anyways, what we're familiar with, is 360, right? But now we also know that one full circle is equal to 2 pi radians. And usually they're called like rad if you write anything. Sometimes you just write 2 pi, and it's just assumed, okay, yeah, so that means radians if you don't have any units there. That's what I mean by unitless. A lot of the times we don't even write units on it. Okay, so this is equal to 2 pi. So that also means, let's say we go halfway around a circle. So halfway, what we used to know it as was 180 degrees, but now we can just take this thing, this 2 pi, and divide it by 2. So 2 pi divided by 2 just gives us pi. Okay, so pi radians is equal to going halfway around your circle. And let's do one more. Let's say we go a quarter of the way through our circle. Normally that was 90 degrees, but now it's going to be a quarter of whatever our full circle was. There we go. So 2 pi was the full length around, or the full rotation. And now if we divide that by 4, we just get pi over 2. Okay? So these are important things to note. Here's like a basic sketch of that. So this is 0 radians. This is pi over 2 radians. This is pi radians. This one's going to be 3 pi over 2. And this is also equivalent to 2 pi once you've traveled one full circle. Okay? So radian measures are especially useful because it's the ratio. Let me write this out. So radians measure the ratio of, and I'll write it out for you guys. So the ratio of arc length drawn out by an angle, okay? And then over, so the ratio of that to the radius of whatever circle you're dealing with. Radius of circle, okay? So let's do an example of this. Let's say we have, I don't know, let me draw a little squiggly line here first. So here's an example. So let's say we have a circle of radius 2, okay? So here's our circle, and let's say it has a radius of 2. Let me just draw that. So r is equal to 2, let's say, okay? And we want to take a fourth of it, okay? Fourth of it, meaning we want to find the arc length of a fourth of this circle, okay? So let's find the circumference of the entire thing. So that would be 2 pi r, and our r is 2. Okay, so c is equal to 4 pi. Okay, so that's the distance all the way around your circle, okay, of that arc length there. And if we take a fourth of that, so a fourth of our circumference is equal to 4 pi over 4, right? We just took our circumference divided by 4, so that just gives us a pi, right? So let's say s, I'm going to call this s here. Our arc length of a fourth of our circle is going to be equal to just a single 1 pi, alrighty? So now, let's say we have another circle, okay? Let's say we have kind of a similar case, but now our r is equal to 3, okay? Again, we want a fourth of it, a fourth of our circumference, okay, to find what is s here, okay? So again, we want to find a fourth of our circumference. So first of all, we have to find our circumference. So that's 2 pi times 3, because I made the radius be 3 on this problem. So this is equal to 6 pi, and a fourth of our c, a fourth of our circumference, which is what we're looking for, would be equal to 6 pi divided by 4, which can be reduced to 3 pi over 2, okay? So now you might be thinking, okay, wait, where are we going with this? So the thing is, we want to kind of show what the top half is telling us. So radian measure is the ratio of an arc length drawn out by an angle divided by the radius of your circle. So what we found for both of these little like mini problems is the arc length drawn out by an angle. So if we take s, which denotes our arc length, right, and divide it by the radius, r, we would get on this left side, we would get pi, because that's what we got for s, divided by r, which was a 2, right? So we got pi over 2 for that. Now let's try it on the right-hand side. So now we'll take s, whatever s was, and divide it by our r for this problem. So this is 3 pi over 2, that was the s we found, divided by r is a 3. So this is the same thing as saying 3 pi over 2 times 1 over 3. The 3's cancel out, and we get, what is this? Pi over 2? What just happened here? So this is exactly what radians tell us, is that we have the ratio of our arc length drawn out by any angle that we rotate. In this case, we said, okay, we're just going to rotate a quarter of the way around our circle, right? So we found the arc length for each of these respective problems when we had a radius of 2 versus a radius of 3. We found the arc length, and then we divided by whatever our r was, right here, right? And we got this same pi over 2, right? Pi over 2 here and pi over 2 there. So that tells us that the constant ratio of arc length to radius, whenever you rotate a quarter of the way around a circle, any circle, meaning like of any radius, you're going to get that same ratio of pi over 2. Okay, and that's especially why radians are a useful measure of rotation.